We're now going to learn about vector fields. I'll start with the definition in two variables. Let D be a set in the xy plane. A vector field on R2 is a function, capital F, that assigns to each point x, y in D a two-dimensional vector f of xy. Vector fields take points x, y and create vectors, so we can represent f of xy in component form as p of xy, q of xy, where p and q are the component functions of f. P and Q are also called scalar fields, while F is the vector field. One of the frustrating things about vector fields is that we can't fully sketch them because it would fill up the whole page. However, we can get the general shape by plotting the vectors for some points. For example, let's look at the vector field f of xy equals y, x minus y. The x component of f is p equals y, and the y component of f is q equals x minus y. This can get a little confusing to keep track of, so that's why it's useful to name the components of f, p, and q. Let's compute f of xy for a few choices of x and y. We can also plot them here. Notice that the vector corresponding to the point x, y starts at the point x, y. Hopefully you're seeing some patterns. When x equals y, q equals 0, so the vectors are horizontal and their length and direction are determined by x. When x equals 0, our vector f is y, negative y, so the vectors get longer as y increases. When y equals 0, we get 0, x, so the vectors are vertical and get longer with x. We can also make vector fields in 3 dimensions. Now we create a function f of xyz that assigns to each point a 3-dimensional vector f of xyz, written in component form as p of xyz, q of xyz, and r of xyz. These are trickier to graph as now we'll need 3 dimensions. I'll show one example using CalcPlot3D. Suppose f of xyz equals y, x minus y, z squared. Notice that this looks the same in the xy plane as our previous example. When we look down on it, we get the same image. As z increases, we see that the vectors get taller. Vector fields exist around us in our everyday life. We can model wind patterns using vector fields, and water currents such as rivers and oceans can be represented using vector fields. We can also use vector fields to study airflow past an object like a rocket. Magnetic fields and force fields are also examples of vector fields. We'll see computations using force fields later on. You've already seen a special type of vector field in this course, the gradient of a function. Recall that if f is a function, the gradient is a vector created from the partial derivatives of f. We've worked with both 2-dimensional and 3-dimensional gradients. For example, consider the function f of xy equals x squared plus y squared. This creates a paraboloid. The partial derivative of f with respect to x is 2x, and similarly, the partial derivative of f with respect to y is 2y. So the gradient of f is the vector field 2x, 2y. I'll sketch it here with the contours of f. Notice that since f is a paraboloid, its contours are circles. Also notice that the gradient vectors are perpendicular to the contours. This is actually a fact we learned before. The gradient vectors are always perpendicular to the level curves of the function. Not every vector field is the gradient of a function. The ones that are have a special name. We say a vector field capital F is conservative if it is the gradient of some scalar function. In other words, capital F equals the gradient of little f. For example, capital F equals 2xy, x squared plus z, y, is the gradient of the function f equals x squared y plus yz. So f is conservative. Naturally, some questions arise. How do we determine if a vector field is conservative? How do we find the scalar function corresponding to it? And most importantly, why do we care? We'll answer these questions in future videos.